Welcome to The Drowsy Astronaut, and tonight we're going to explore wormholes, those mysterious tunnels through space, sometimes described as gateways that bend both distance and time, hinting at journeys stranger than imagination. Before we start, I'd love to know where you're listening from. It's always comforting to picture people from far-off places gathering together under the same sky. And as always, you can relax, drift off, or even work along with it. There's absolutely no pressure. Whether you stay for 2 hours or fall asleep halfway through, that's exactly what this is meant for. What we'll do is first experience a wormhole, imagining the journey through one. Then we'll explore the science behind it with clarity and depth, uncovering the possibilities these strange structures might hold for us. We'll talk about space and time being connected, about Einstein's equations, and I'll explain everything in plain language, building your understanding piece by piece, never rushing the details. By the end, whether you've drifted off or stayed awake, you'll have traveled across the galaxy, visited distant stars, moved through time itself, and understood the physics that makes these journeys theoretically possible. But for now, just get comfortable, let your breathing slow down, and picture yourself floating in deep space, far from any star, watching distant galaxies drift by like clouds. The universe is unimaginably vast, so large that distance becomes almost meaningless. The nearest star to our sun is over 4 light years away, meaning light itself takes 4 years to cross that gap. To reach that star with our current technology would take tens of thousands of years. Generations of humans living and dying aboard a ship, never seeing the destination, their descendants finally arriving at last. The Milky Way galaxy stretches 100,000 light years across, containing billions of stars, most of which humanity will never visit, never explore, never even see clearly through our telescopes. And beyond our galaxy lie billions more, separated by millions of light years. Distances so vast that even traveling at light speed, the universe's ultimate speed limit, we could never reach them in a human lifetime. This is the problem that haunts anyone who dreams of exploring space. The universe is beautiful, full of wonders, but almost entirely unreachable by conventional means, locked away by distance. But what if there were shortcuts? Tunnels through space itself? Passages that could connect distant points, letting you step from one location to another without crossing all the space in between. This is the idea of a wormhole, and it sounds like science fiction. But the mathematics of physics actually allows for them. And tonight we'll explore what they are, how they work, and what traveling through one would feel like. Imagine standing before a doorway that opens onto a star system 5,000 light years away. You step through, and in moments, you're there, having crossed a distance that would normally take millennia to traverse. That's the dream, the beautiful possibility that wormholes represent, and even if we never find one, even if they exist only in equations, thinking about them teaches us how space and time really work. To understand wormholes, we need to think about space differently, not as empty nothingness, but as something real, something with structure, something that can bend and curve and possibly even fold. Space and time are woven together into what physicists call spacetime. A 4-dimensional fabric that contains everything, every star, every planet, every moment of history, all woven into one continuous tapestry. Massive objects create curves in this fabric, like a bowling ball placed on a stretched rubber sheet. The ball creates a dip, a depression, and other objects roll toward it, following the curve that the mass has created in space-time. This bending of space-time is what we call gravity, not a force pulling objects together, but objects following the natural curves in space-time, moving along paths that bent geometry creates around them. When you drop something, it falls because Earth bends space-time around it, and the object follows that curve, moving through bent space, and we perceive that motion as falling, as gravity pulling downward. The more massive an object, the deeper it bends space-time. Earth creates a modest dip, the Sun creates a deeper one, and black holes create infinitely deep wells, points where space-time curves so extremely that nothing can escape. Time also behaves strangely near massive objects. It slows down, ticking more slowly the deeper you go into a gravitational well, and this has been measured. Clocks on GPS satellites run slightly faster than clocks on Earth's surface. If you stood near a black hole, time would slow dramatically for you. And if you watched someone far away, they would seem to move incredibly fast, aging years while you experienced minutes, because time flows differently at different points in curved space-time. This is the foundation we need to understand wormholes, because if space-time can bend, curve, and stretch, then maybe it can fold, bringing distant points close together, creating shortcuts through the fabric itself. Imagine space-time as a flat sheet of paper, and 2 points on opposite sides of the sheet are far apart if you travel across the surface, but if you fold the paper so those points touch, suddenly they're next to each other. A wormhole would be like poking a hole through that fold, creating a tunnel, a bridge between the 2 points, and if you could travel through that tunnel, you'd cross from one side to the other instantly, bypassing all the space in between. This is the idea, beautiful and simple in concept, but the reality is far more complex, because space-time isn't paper, it's dynamic, governed by Einstein's equations, and creating or maintaining a wormhole requires conditions so extreme. Tonight we're going to experience one first, before diving into all the complications. We're going to imagine what it would be like to approach a wormhole, to enter it, to travel through its throat, and to emerge somewhere completely different, light years away. Then, we'll understand the science, we'll explore the challenges, and we'll dream about what they might mean for humanity's future, for our ability to explore the cosmos, for our place in the universe. So picture yourself in a spacecraft drifting through deep space, and ahead of you, space itself begins to look strange, distorted, bent in ways that shouldn't be possible, warping the starlight into impossible patterns. Your instruments begin to register something unusual, massive gravitational readings. But there's no star ahead, no planet, no black hole that you can see, just empty space that somehow bends light around an invisible sphere. As you drift closer, the distortion becomes more pronounced. Stars behind this region stretch into arcs, their light bending around something, colours shifting from blue to red and back, creating rings of starlight that circle a dark sphere. This is a wormhole mouth, and it doesn't glow or shine. It's not a physical object, but a region where space-time is curved so extremely that it forms a tunnel, a passage connecting this location to somewhere impossibly distant. You're approaching something that shouldn't exist according to common sense, but mathematics predicted it. And here it is, real and waiting, a doorway through the fabric of reality itself, offering passage to places no conventional ship could ever reach. The wormhole mouth appears as a perfect sphere, perhaps a kilometer across, and as you approach, you can see through it, distorted light from the other side reaching your eyes, showing you a glimpse of your destination before you even enter. The stars visible through the wormhole look wrong, unfamiliar constellations, patterns you've never seen before, because they're the stars of a region thousands of light years away, their light traveling through the tunnel and reaching you here, bridging the vast distance. Around the mouth, space-time is severely bent, and the stars behind the wormhole appear to wrap around it, creating a spherical mirror effect. Light paths curving so strongly that you see multiple distorted images of the same stars from different angles. Your spacecraft's sensors are reading gravitational forces, but they're strange, not pulling you inward like a black hole would, but creating complex tidal forces, pulling and pushing in different directions, the signature of a tunnel through space-time rather than a pit. You make the decision to enter, to cross through. Your engines fire briefly, adjusting your trajectory, and you drift toward the mouth, your speed measured and careful, because nobody knows exactly what passing through will feel like, what forces you'll experience inside the throat. As you cross the threshold, everything changes in an instant. The stars behind you suddenly distort violently, stretched and compressed, and the familiar constellations of your home region vanish, replaced by the strange view through the tunnel, light from both ends mixing in impossible ways. You're inside now, floating in the throat of the wormhole, and the walls aren't physical, they're just regions of extremely curved space-time, bending light and matter along paths that form a tube, a passage connecting two distant points in the universe. Looking back toward the entrance, you see the stars you just left, but they're compressed into a shrinking circle, growing smaller as you drift forward, your home region of space receding through the tunnel, kilometers away but connected by this impossible bridge. Looking forward toward the exit, you see the destination growing. A circle of unfamiliar stars expanding, growing brighter, filling more of your view as you drift through the throat, carried by momentum through this tunnel in space-time. The throat itself is dark, not black, but simply empty. No stars exist here, no matter, just the curved geometry of space-time forming a tube, and the only light comes from both ends. Photons that entered the wormhole and are traveling through it, just like you. Time feels strange inside the throat, elastic and uncertain. Your instruments show seconds passing normally, but your perception feels off, as if time is stretching or compressing, and you can't quite tell if you've been inside for moments or much longer. The walls of the wormhole, if you can call them walls, shimmer with gravitational distortions, space-time bent so severely that light paths spiral around the throat, and you see strange reflections, multiple images of your ship from different angles, light bouncing through the curved geometry. Your body experiences tidal forces, gentle but noticeable. Your head and feet are slightly different distances from the center of the throat, and gravity tries to stretch you, pulling your head one way and your feet another. A mild spaghettification effect that's uncomfortable but not dangerous in this stable wormhole. The throat is perhaps only a few kilometers long, much shorter than the thousands of light years it connects, and you're drifting through at maybe 100 meters per second, so the journey will take less than a minute, a tiny passage through space that bypasses an enormous distance. You notice something beautiful and strange ahead. The exit circle is filled with the light of a new sky, stars you've never seen, and you can make out individual stars now, close and bright, clearly visible, even from inside the wormhole, their light streaming through the tunnel toward you. One star in particular is brilliant, bluish white and large, much brighter than the sun, and you realize it's close to the exit, perhaps only a few light years away, dominating the sky beyond the wormhole, a beacon welcoming you to this distant region of space. The exit approaches rapidly now, the circle expanding to fill your view, and you feel a strange anticipation, knowing that in moments you'll emerge into a region of space that's thousands of light years from Earth, farther than humans have ever traveled, crossing a distance that would take conventional ships millennia. Your instruments show the gravitational readings changing, the tidal forces shifting, and you brace yourself, not sure what crossing back out into normal space will feel like, whether there will be a jolt or a smooth transition, whether time will snap back to normal or ease gradually. And then you're through, crossing the exit threshold, and suddenly the distortions vanish. Space-time flattens back to normal and you're floating in open space, surrounded by unfamiliar stars, the wormhole mouth behind you now, looking just like the entrance did, a sphere of distorted space-time. But everything else is completely different. The constellations are wrong, the stars are in unfamiliar patterns, and that brilliant blue star dominates the sky so bright that your ship's windows automatically darken to protect your eyes, filtering the intense light. You've crossed 5,000 light years in less than a minute, a journey that light itself would take 5,000 years to complete, and you did it by taking a shortcut, bypassing all that space by traveling through a tunnel in space-time rather than across normal space. Looking back at the wormhole mouth, you can see through it to your home region, the familiar stars of human space visible through the tunnel, a window back to where you came from, and you realize you could return just as easily, stepping back through and emerging near Earth in moments. This is the power of a wormhole, the reason they fascinate scientists and dreamers. They defeat distance, they make the vast universe suddenly accessible, they turn impossible journeys into brief passages, transforming our relationship with space itself. You drift away from the wormhole, orienting your ship toward the bright blue star, and you begin scanning your instruments, picking up planets, asteroids, a solar system that's never been explored, that's so far from Earth that conventional missions could never reach it. Yet here you are. The star is a young giant, perhaps 10 million years old, much hotter and brighter than our sun, burning blue-white with fierce intensity, and your sensors detect 6 planets orbiting it, including 2 rocky worlds in the habitable zone, where temperatures might allow liquid water on the surface. One of those planets shows signs of an atmosphere, nitrogen and oxygen, spectral lines indicating clouds, weather, and your heart races, because this is exactly the kind of world humanity has been searching for, a potentially habitable planet, a place where life might exist or where humans could one day live. And you're here, able to study it because a wormhole brought you, crossing thousands of light years in moments, making this discovery possible, proving that if wormholes exist, if we can find them or build them, the entire galaxy becomes our neighborhood, every star system potentially reachable. You send a probe toward the planet, initiating scans, and you turn your ship back toward the wormhole, preparing to return home with this incredible news, knowing that others will follow, that this wormhole has just opened an entire region of space to human exploration. As you approach the wormhole mouth again, you marvel at how ordinary it looks. Just a sphere of distorted space, no more intimidating than it was before. But now you know what lies beyond. You've experienced the passage, and it feels less like magic and more like a tool, a piece of cosmic infrastructure waiting to be used. You enter the mouth, and the journey back is just as brief. Drifting through the throat, watching your home stars grow larger, and moments later you emerge back near Earth, having completed a round trip across thousands of light years in less than 5 minutes. A journey that fundamentally changes what's possible for humanity. This is the dream, the vision that wormholes inspire. Not just one tunnel, but dozens, hundreds, scattered through the galaxy, connecting stars and systems, creating a network that turns the Milky Way into a connected web, every part accessible, every world reachable. Imagine what this would mean for civilization, for science, for exploration, for humanity's future. And as you drift back toward Earth, you begin to understand why physicists study wormholes so intensely, why they matter even if we've never found one, why the possibility alone reshapes our understanding of what's achievable. Imagine not just one wormhole, but dozens scattered throughout the galaxy. A network connecting key locations, strategic points near important stars, nebula, research sites, and habitable worlds, transforming the Milky Way into a connected system. Each wormhole mouth would be positioned deliberately, one near Earth, one at the galactic center, one in the Orion Nebula, another near dense star clusters, creating a cosmic subway system where travelers could hop between distant locations in minutes rather than millennia. The Orion Nebula, a vast stellar nursery 1,500 light-years away, would normally require 15 centuries to reach at light speed, but with a wormhole, you step through near Earth and emerge floating above glowing gas clouds, watching stars being born in real time. From there, another wormhole could connect to Sagittarius A star, the supermassive black hole at our galaxy's center, 26,000 light-years away, a journey that would take 26 millennia at light speed, reduced to a brief passage through a tunnel. You could watch the galactic center's chaotic environment safely. Stars orbiting the black hole at incredible speeds, gas swirling into the accretion disk, and then step back through the wormhole to Earth, returning home for dinner after witnessing one of the most extreme environments in the universe. Another wormhole might connect to the Andromeda Galaxy, 2.5 million light-years away, our nearest large galactic neighbor, a journey so vast that light takes 2.5 million years to cross, but through a wormhole, you'd arrive in moments. Emerging in Andromeda, you'd see a completely different galaxy, 1 trillion stars arranged in different patterns, spiral arms tilting at unfamiliar angles, and looking back, you'd see the Milky Way as a distant smudge of light, a view that only telescopes have captured from Earth. With multiple wormholes connecting both galaxies, humans could live in Andromeda, working, exploring, building colonies, and return to visit family on Earth whenever they wanted, the vast intergalactic distance rendered meaningless by the network, distance defeated by geometry. The Pleiades cluster, a young group of hot blue stars 400 light-years away, would be another perfect hub, and a wormhole there would let scientists study stellar evolution up close, watching how stars form, evolve, and interact in dense environments, visiting regularly to monitor changes over years and decades. Imagine scientists commuting to work in the Pleiades, stepping through a wormhole each morning, conducting research on stellar physics, then returning home to Earth by evening, the 400 light-years crossed twice daily as casually as driving to an office. Colonies could be established on habitable planets orbiting distant stars, each connected by wormholes to Earth and to each other, creating a galactic civilization where distance no longer isolates, where every human settlement, no matter how far, remains in constant contact with the rest. Trade would become instant, shipping resources and goods through wormholes, rare elements from one star system, agricultural products from another, technology and culture flowing freely across light years, knitting the galaxy's human settlements into one unified economy and society. Military strategy would change completely, because wormholes could be defended or blocked, and controlling key wormhole mouths would be like controlling vital straits or mountain passes, strategic points that determine who can travel where, who can access which regions of space. A single wormhole mouth could be moved hypothetically, placed on a spacecraft and transported to a new location. And this means wormholes aren't just static infrastructure, they're flexible, repositionable, able to connect new regions as exploration expands into uncharted areas of the galaxy. Imagine explorers discovering a fascinating exoplanet 5,000 light-years away. And instead of establishing a colony that's isolated for centuries, they bring a wormhole mouth there, connect it to the network, and suddenly that world is just a step away from Earth, integrated immediately into human civilization. The galaxy would feel smaller, more intimate, every star within reach, every phenomenon accessible, and humanity's sense of home would expand from one planet to dozens, from one star system to hundreds, the species spreading across the Milky Way while remaining connected, united by tunnels through space-time. Communication would be instantaneous across the network, because signals could be sent through wormholes, avoiding the speed of light delay that normally makes conversations with distant spacecraft painfully slow, taking years for messages to cross interstellar space, making real-time dialogue impossible. With wormholes, you could have a video call with someone on a planet 10,000 light-years away, talking normally, no delay, because the signal travels through the tunnel, bypassing all that space, and suddenly the galaxy's human settlements can coordinate, govern, and maintain culture as if they were neighboring cities. Science would advance at incredible speed, because phenomena that we can currently only observe from light years away could be studied up close, visited repeatedly, monitored continuously, allowing detailed research on supernovae, black holes, neutron stars, exotic objects that conventional travel makes inaccessible. You could witness a supernova from a safe distance, watching a massive star explode, studying the shockwave, the neutron star formation, the nucleosynthesis that creates heavy elements, and then return home to analyze your data, all in a single research trip, what would otherwise require generations of patient observation with telescopes. The network would grow over time as more wormholes are discovered or created, each new connection opening another region of space, and the map of the galaxy would transform from a spatial diagram into a network diagram with nodes and connections, distances measured not in light years but in number of wormhole hops required to reach a destination. Travelers would plan routes through the network, perhaps Earth to Vega, to Betelgeuse, to Sagittarius A star, hopping through 3 wormholes to reach the galactic center, the entire journey taking 15 minutes, crossing 26,000 light-years by connecting through intermediate points in the web. Young people might spend a gap year traveling the network, visiting a dozen different star systems, experiencing the diversity of galactic environments, from dense clusters to sparse outer regions, from young hot stars to ancient red giants, all connected by wormholes that make this grand tour possible. And as you imagine this network, this web of connections across the galaxy, you begin to wonder about time, about whether wormholes could connect not just different places, but different moments, whether you could step through and emerge not just elsewhere, but elsewhen. Space and time are woven together, inseparable parts of space-time. So if wormholes can connect distant places, it's natural to wonder whether they might also connect distant times, creating passages not just across space but through the fourth dimension, allowing travel to past or future. The idea sounds impossible, like pure fantasy, but the mathematics of general relativity actually allows this under certain conditions. If a wormhole's two mouths experience time at different rates, which can happen through time dilation, the slowing of time near massive objects, or during high-speed travel. Here's how it could work in simple terms. Imagine you have a wormhole with two mouths, initially side by side, and you load one mouth onto a spacecraft, accelerating it to near light speed, while the other mouth stays on Earth, stationary. Due to time dilation, time passes more slowly for the moving mouth, and when the spacecraft returns to Earth after traveling at high speed for 10 years of Earth time, only 1 year has passed for the moving mouth, creating a time difference between the two mouths. Now the wormhole connects not just two places, but two times. Step through the Earth mouth now, in the year 2100, and you emerge from the moving mouth in 2091, because that mouth is 9 years behind, experiencing time more slowly due to its high-speed journey through space. You've traveled backward in time by stepping through space. And this isn't science fiction, it's a legitimate prediction of general relativity, though whether nature actually allows this, whether stable time travel wormholes can exist, remains a deep question with no definitive answer yet. What would it feel like to step through such a wormhole? To enter in 1 year and emerge in an earlier year, to walk from future to past through a doorway. The transition might feel completely normal, no different from crossing space. You step through, and when you emerge, you check your watch, and the date confirms you've moved backward, you're in the past. Standing on Earth 9 years ago, before you ever entered the wormhole. Looking around, everything is subtly different. Buildings that don't exist yet in your time are missing. Technology is less advanced. People you know are younger, and you're walking through a world that, from your perspective, already happened. Events that you remember but are only now occurring around you. You could observe events from your own past, standing in the crowd at a historical moment, watching it unfold. Or you could try to interact, to change things. And here the physics becomes deeply strange, because altering the past creates paradoxes. The grandfather paradox is the classic example. If you travel to the past and prevent your grandparents from meeting, you would never be born. But if you're never born, you can't travel to the past to prevent their meeting, so do you exist or not? Physics doesn't have a clear answer, but several possibilities exist, different ways the universe might handle this problem, different frameworks that might allow time travel without creating logical contradictions. One possibility is the Novikov self-consistency principle, which says that if time travel is possible, then events must be self-consistent, meaning you can't change the past, because your attempt to change it was always part of what happened, creating a closed loop where everything fits together without paradox. In this view, if you travel to the past to prevent something, you'll find that you fail, or that your actions inadvertently cause the very thing you tried to prevent, ensuring the timeline remains consistent, the past unchangeable because any change you make was always part of history. Another possibility is the many worlds interpretation, where traveling to the past creates a new timeline, a branch of reality where your changes occur while the original timeline continues unchanged, splitting the universe into parallel histories that coexist without affecting each other. In this view, you could change the past, but you'd be changing a different version of it. You'd create an alternate history where your actions matter, but your original timeline remains intact, your home universe unaffected by what you do in the past of a parallel reality. A third possibility is that nature simply prevents time travel, that whenever conditions arise that would allow backward time travel, something intervenes, quantum effects or unknown physics that destabilize the wormhole, preventing the time loop from forming, protecting causality from violation. Physicist Stephen Hawking called this the chronology protection conjecture, the idea that the laws of physics contain some mechanism, perhaps related to quantum mechanics, that prevents time machines from forming, ensuring that cause always precedes effect, that the past remains safely in the past, unchangeable and protected from future interference. We don't know which of these is correct, or whether time travel through wormholes is even possible. But the fact that serious physicists consider it, that the mathematics allows it, tells us that time is stranger than everyday experience suggests, more flexible than we instinctively believe. Imagine standing before a wormhole that leads to Earth's past, to your childhood, to historical eras, to moments you've only read about, and you feel the pull of curiosity, the desire to see, to know, to experience what was. Even as you wonder about the implications, the responsibilities, the dangers of stepping through. If such wormholes existed, what would humanity do with them? Would we use them to study history, to witness events firsthand, sending historians through to record what really happened, to answer questions that documents leave uncertain? Or would we try to change things, to prevent disasters, to save lives, to correct mistakes, and would the universe allow that? Or would our attempts always fail, folded into the timeline in ways that preserve consistency, teaching us that the past is fixed, immutable despite our access to it? These questions have no answers yet, because we've never found a time travel wormhole, never tested what happens when past and future connect, but thinking about them pushes our understanding of time, forces us to question assumptions about causality, about the nature of reality itself. For now, time travel wormholes remain theoretical, mathematical possibilities, but they remind us that space-time is deeply strange, that time is not the simple forward flow we experience, but something more complex, potentially navigable, possibly flexible in ways we haven't yet discovered. Now let's understand the science more deeply, gently, building on what we've experienced, because to truly appreciate wormholes, we need to know what Einstein discovered about gravity, about space-time, and why his equations allow these cosmic tunnels to exist, at least mathematically. In 1915, Einstein published his general theory of relativity, and it fundamentally changed our understanding of gravity, showing that what we experience as gravitational force is actually the curvature of space-time caused by mass and energy, a geometric phenomenon rather than a force. Massive objects like stars and planets bend space-time around them, creating curves, and other objects move along those curves, following what mathematicians call geodesics, the straightest possible paths through curved space-time, which appear to us as curved trajectories through space. The equations Einstein wrote describe how matter curves space-time, and how that curvature affects the motion of matter and light, creating a feedback loop where matter tells space-time how to curve and space-time tells matter how to move, a beautiful self-consistent system. Within those equations, physicists found solutions corresponding to black holes, regions where space-time curves so extremely that it forms a one-way trap, a point of no return called an event horizon, beyond which nothing can escape, not even light, because all paths lead inward toward the central singularity. But there were other solutions, stranger ones, mathematical wormholes called Einstein-Rosen bridges, found in 1935, showing that under certain conditions, space-time could curve in such a way that it creates a tunnel, a bridge connecting two distant regions, or even two separate universes joined by this geometric structure. These solutions were fascinating, but they had a fatal problem. They were unstable, collapsing almost instantly, and anything trying to pass through would be crushed by tidal forces as the throat pinched shut faster than light could traverse it, making these natural wormholes useless for travel. To keep a wormhole open, you need something exotic, matter or energy with negative mass or negative energy density, something that pushes space-time outward instead of pulling it inward, counteracting the natural tendency to collapse, propping the tunnel open like scaffolding supporting a mine shaft. Negative energy sounds impossible, contradicting everything we know about matter. But quantum mechanics offers a hint that it might exist through something called the Casimir effect, where two metal plates placed very close together in a vacuum experience a tiny attractive force. Because quantum fluctuations create negative energy density between the plates. The effect is real, measurable, confirmed in laboratories. But the amount of negative energy is incredibly tiny, nowhere near enough to stabilize a human-sized wormhole, requiring amounts that might be impossible to generate, though we can't say with certainty that it's fundamentally forbidden. So the question remains open, whether exotic matter exists in sufficient quantities, whether advanced civilizations could generate or collect it, whether nature provides it somewhere, in some extreme environment we haven't explored, or whether wormholes remain forever theoretical, allowed by mathematics but forbidden by physics. There are different types of wormholes in the mathematics. Schwarzschild wormholes that connect two universes but collapse before anything can pass, and Morris-Thorne wormholes that remain open if exotic matter exists, and Lorentzian wormholes that could theoretically connect different times as well as different places. Physicists have studied whether wormholes could form naturally, perhaps in the first moments after the Big Bang, when the universe was incredibly hot and dense, when quantum fluctuations were enormous, possibly creating tiny wormholes that survived and grew, or remained microscopic, scattered through space like invisible threads connecting distant points. These primordial wormholes, if they exist, might be incredibly small, smaller than atoms connecting points at quantum scales, and some theories suggest they might link entangled particles, that quantum entanglement, the spooky connection Einstein puzzled over, might actually involve microscopic wormholes connecting the particles through space-time. This idea is called ER equals EPR, connecting Einstein-Rosen bridges to Einstein-Podolsky-Rosen entanglement, suggesting that when two particles are entangled, sharing quantum states instantly across any distance, they might be connected by a tiny wormhole, a geometric link through space-time that explains the correlation without requiring faster-than-light communication. It's speculative, not proven, but it hints at deep connections between quantum mechanics and gravity, between the very small and the very large, between particle physics and the structure of spacetime, suggesting that wormholes might be more fundamental to reality than we realize, woven into the fabric at scales we can't directly observe. Black holes might also hide wormholes at their centers, where Einstein's equations predict a singularity, a point of infinite density. But some physicists wonder whether that singularity might actually be a wormhole throat, a passage to another region of spacetime or another universe, though crossing it would still be impossible because you'd be crushed by tidal forces before reaching it. Some solutions involve rotating black holes, called Kerr black holes, where the singularity isn't a point but a ring. And mathematically, you might pass through the ring without hitting it, potentially emerging somewhere else. Though whether this works in reality or only on paper remains unknown, untested, purely theoretical. The mathematics says many things are possible, but nature might impose restrictions that the equations don't reveal, quantum effects or unknown physics that prevent certain solutions from existing, and until we observe a wormhole, we won't know which mathematical possibilities correspond to real structures in the universe. This is where we are, balanced between possibility and uncertainty. The equations allow wormholes, but we've never seen one, and whether they exist naturally, whether they can be created, whether they're stable enough for travel, all remain open questions that future science must answer through observation, experiment, or deeper theoretical understanding. If nature doesn't provide stable wormholes, could an advanced civilization build one? Could sufficiently advanced technology manipulate space-time itself, gathering exotic matter, generating negative energy, engineering the geometry to create and maintain a traversable tunnel connecting distant regions? The energy requirements would be staggering, beyond anything humanity can currently produce. Some calculations suggest you'd need negative energy equivalent to the mass of Jupiter, or more, concentrated in a small region, and generating, containing, and shaping that energy would require capabilities far beyond our current technology. On the Kardashev scale, which measures civilizations by energy use, a Type 1 civilization harnesses all the energy of its planet, Type 2 harnesses its star's entire output, and Type 3 harnesses a galaxy's energy, and building wormholes might require Type 2 or Type 3 capabilities, civilizations millions or billions of years more advanced than humanity. Such a civilization might manipulate stars, build megastructures, harness black holes, and possibly generate exotic matter through quantum engineering, processes we can't even imagine. And for them, creating a wormhole might be a major project, but not impossible. Similar to how we build bridges or tunnels through mountains. They might start by creating a micro wormhole in a laboratory, using incredibly powerful energy fields to curve space-time at quantum scales, generating negative energy through advanced versions of the Casimir effect. And if they succeed, they'd have a tiny tunnel, perhaps connecting 2 points in the lab, invisible but detectable through quantum measurements. Then they'd need to enlarge it, feeding it energy and exotic matter, stabilizing the throat as it grows, expanding it from microscopic to macroscopic scales, perhaps using feedback loops where the wormhole's own geometry helps stabilize itself, self-reinforcing patterns in space-time that prevent collapse once the structure reaches a certain size. Eventually, they'd have a human-sized wormhole, stable and traversable, one mouth in the laboratory, and they could move the other mouth by attaching it to a spacecraft, transporting it to another location, perhaps another star system, and when the ship arrives, the wormhole connects the two locations, instant travel between them established. Over time, they could build a network, creating many wormholes, positioning them strategically across their region of the galaxy, and eventually they'd have the infrastructure we imagined earlier, a web of connections transforming space travel, making their civilization truly galactic, unified across light years by tunnels through space-time. For humanity, this is distant future. We can barely leave our planet. We've only sent probes to the edge of the solar system and manipulating space-time itself, generating exotic matter, building wormholes. All of this lies centuries or millennia ahead, requiring fundamental advances in physics, engineering, and energy generation that we can only dimly imagine today. But thinking about it teaches us what's possible, what goals we might reach, and it gives us a vision of what an advanced civilization might do, how they might spread across the galaxy, and if we ever encounter such a civilization, we might find they've already built wormhole networks, cosmic infrastructure connecting their empire. Detecting a wormhole, if one exists, would be challenging but possible. Gravitational lensing would reveal it, light from background stars bending around it in distinctive patterns, and gravitational wave detectors might pick up unique signatures if a wormhole forms or if mass passes through one, ripples in space-time that differ from black holes. Astronomers are always analyzing data, looking for anomalies, and if a wormhole exists in our galaxy, we might eventually find it through careful observation, noticing patterns in starlight or gravitational waves that match theoretical predictions, confirming that these structures exist not just in mathematics but in reality. The discovery would be profound, revolutionary, because it would mean the universe is navigable, that shortcuts exist, that the barriers of distance might be overcome, and humanity would immediately begin planning missions to study it, to test whether it's stable, whether it's traversable, whether we could send probes through and eventually follow ourselves, taking our first steps toward truly galactic exploration. Even if we never find or build one, studying wormholes matters, because it pushes our understanding of space-time, of gravity, of quantum mechanics, forcing us to think deeply about the universe's structure, about what's possible, about how reality works at its most fundamental level. Wormholes sit at the intersection of our grandest theories, connecting general relativity and quantum mechanics, touching questions about causality, time, entropy, and information, and trying to understand them fully requires unifying these theories, solving problems that have puzzled physicists for decades, pushing toward a theory of quantum gravity. So whether they exist or not, wormholes serve as a tool for learning, a thought experiment that reveals deep truths, a mathematical structure that guides our exploration of physics, and imagining them, studying them, we come to understand space and time more deeply, preparing for whatever discoveries future centuries might bring. Imagine a future where your descendants find or build a wormhole, where humanity spreads across the galaxy not through slow generation ships, but through instant passages, where every human settlement remains connected, where the stars are no longer impossibly distant, but merely separated by brief journeys through tunnels in space-time. In that future, a child on a planet orbiting a star 5,000 light-years away might visit Earth on vacation, stepping through a wormhole and emerging near the sun, seeing humanity's homeworld with their own eyes, walking on the planet where our species evolved, connecting personally with our origin despite the vast distance. Scientists in that future would have access to the entire galaxy, studying supernovae up close, monitoring black holes directly, exploring nebulae from within, discovering thousands of new phenomena that we can only observe remotely, limited by distance and the speed of light, unable to reach the wonders we glimpse through telescopes. And perhaps they'd discover that wormholes are natural, common even, scattered throughout the universe, remnants of the Big Bang or products of black hole collisions, and they'd map this hidden network, revealing that the cosmos has always been more connected than we realized, that nature provided the shortcuts, waiting for us to find them and learn to use them, opening the galaxy to exploration. Or perhaps they'd find that wormholes are rare, requiring immense effort to create, that each one is a triumph of engineering, a mega project spanning decades, and wormholes would be precious, carefully maintained, strategically placed, each connection representing generations of work, each passage through one a reminder of what it took to defeat distance, to connect the scattered outposts of human civilization across the vast galactic expanse. Either way, the future might hold answers to questions we can only speculate about tonight. Whether wormholes exist, whether we can make them, whether we can travel through them, and perhaps, centuries from now, historians will look back at this moment, at our speculation, and smile, knowing what we couldn't, having the answers we can only dream about. For now, we float here in imagination, having travelled through wormholes in thought, having crossed the galaxy, having moved through time, and though we haven't left our room, haven't moved through space, the journey has taken us somewhere, expanded our sense of what's possible, what space and time really are, what future generations might achieve. As we prepare to continue this journey, you might feel yourself drifting, your thoughts slowing, your breathing deepening, and that's perfectly natural because we've travelled far tonight, crossed immense conceptual distances, and like any journey, it's tiring, inviting rest, encouraging you to let these ideas settle into dreams where space and time bend and fold, where you drift through cosmic tunnels travelling forever. If wormholes exist naturally, where would we find them and what would they look like? Hidden in empty space, or lurking near black holes, or scattered through the galaxy as remnants of cosmic events, invisible until we know exactly what signs to search for. One possibility is that they formed in the early universe, during the Big Bang's first fractions of a second, when space-time itself was churning, when quantum fluctuations were enormous, creating tiny bubbles and structures in the fabric, some of which might have become wormholes, frozen into the expanding universe. These primordial wormholes would be ancient, older than stars, perhaps microscopic, connecting random points in space, or perhaps some grew over billions of years, fed by energy and matter, expanding from quantum size to macroscopic scales, becoming traversable tunnels that exist today, waiting to be discovered. They might drift through space like invisible threads, unattached to anything, moving through the galaxy, and occasionally one might pass near Earth, close enough to detect its gravitational effects, causing slight anomalies in satellite orbits or subtle distortions in starlight that careful observation might reveal. Another possibility is that wormholes form during extreme cosmic events, when black holes collide, merging in cataclysmic impacts that release enormous energy. Perhaps the collision briefly creates conditions where space-time tears and reconnects differently, forming a wormhole that survives after the black holes combine, a scar in space-time from the violent merger. Gravitational wave detectors like LIGO have observed many black hole mergers, recording the ripples they create in space-time, and scientists analyze these signals carefully, looking for unusual features that might indicate something other than a simple merger. perhaps signatures that would point to wormhole formation during the collision. So far, nothing conclusive has been found, but we've only begun to observe gravitational waves. We've detected dozens of events from thousands of candidates, and as our instruments improve, as we observe more mergers, we might find anomalies that suggest wormholes form in these extreme conditions, revealing a natural production mechanism. Some theorists suggest wormholes might exist at the centers of galaxies, near the supermassive black holes that sit at galactic cores, where space-time is so extremely curved that unusual structures might form, hidden in the intense gravitational environment, masked by the black hole's overwhelming presence, but potentially detectable through careful analysis. If a wormhole existed near Sagittarius A star, our galaxy's central black hole, stars orbiting nearby would show subtle anomalies in their paths, deviations from what pure black hole gravity would predict, and astronomers constantly monitor these orbits, measuring positions to incredible precision, looking for any hint of additional gravitational sources or unexpected space-time structures. Another place to look is near neutron stars, incredibly dense objects where a teaspoon of matter weighs as much as a mountain, where space-time curves dramatically. And some theories suggest that in such extreme environments, quantum effects might stabilize tiny wormholes, creating structures that persist in the intense gravitational field surrounding these collapsed stars. Binary neutron stars, two neutron stars orbiting each other, are particularly interesting, because when they spiral inward and collide, they create even more extreme conditions, briefly reaching densities and energies where space-time might behave in exotic ways, potentially forming transient wormholes that exist for microseconds before collapsing, too brief for travel but detectable through gravitational waves. We haven't detected any of this yet, but we're looking. Every gravitational wave signal is analyzed, every unusual orbital pattern investigated, and astronomers remain alert for signatures that don't match known objects, for anomalies that might reveal wormholes hiding in plain sight, camouflaged among ordinary cosmic phenomena. The challenge is that wormholes might look similar to black holes. Both bend light, both create gravitational lensing, and distinguishing them requires careful observation of subtle differences, noticing that light passes through a wormhole rather than disappearing, that objects can emerge from the other side rather than vanishing forever beyond an event horizon. One distinctive signature would be light from both sides. If you observe a wormhole, you'd see light from behind it, lensed around the mouth, but also light from the other end, emerging through the tunnel, creating a complex pattern where images from two distant regions of space overlap, mixed together by the wormhole's geometry in ways that black holes never produce. Another signature might be matter flowing through, gas or dust entering one mouth and emerging from the other. And if we observed this, if we saw material disappear in one location and reappear light years away instantaneously, we'd have strong evidence for a traversable wormhole, a structure actually connecting distant points through space-time, rather than just bending light around a massive object. Some physicists have proposed looking for wormholes in cosmic ray patterns, because high-energy particles traveling through the galaxy might occasionally pass through a wormhole, and their arrival directions wouldn't match their sources, creating anomalies in the cosmic ray map that could hint at shortcuts these particles took through space-time rather than traveling directly across light years of ordinary space. The search continues, data accumulating, astronomers and physicists analyzing every new observation, And perhaps one day someone will notice something, an anomaly that matches predictions, a gravitational lens that behaves wrong, an orbital deviation that suggests hidden structure, and the discovery will change everything, proving that wormholes exist not just in theory, but in reality. Until then, we can only imagine, speculate, and prepare, developing the mathematics, refining our predictions, building better instruments so that when we finally find one, if we find one, we'll recognize it, we'll understand what we're seeing, and we'll know immediately that the universe has revealed one of its deepest secrets, a passage through space-time itself. Imagine the announcement, the press conference where scientists reveal the discovery, showing images of the wormhole, explaining how they found it, describing the observations that confirmed it, and the world reacting with wonder and excitement, realizing that the universe is more connected than we thought, that shortcuts through space might actually exist, waiting for us to learn how to use them. That moment might be centuries away, or it might come tomorrow. Someone analyzing data right now might be looking at the signature without realizing it. And years from now, after careful verification, the discovery will be announced, and humanity's relationship with space will change forever, distance becoming less absolute, the cosmos opening in new ways. To understand wormholes better, it helps to compare them to related structures, black holes and white holes, objects that also involve extreme curvature of space-time, but with different properties, different geometries, different rules about what can pass through them and in which directions matter and light can flow. Black holes are probably familiar, objects where gravity is so strong that nothing escapes. Matter and light cross the event horizon, a one-way boundary, and everything inside falls toward the singularity at the center, crushed to infinite density, and information about what fell in seems to be lost forever, creating puzzles about quantum mechanics that physicists still debate intensely today. The event horizon is the key feature, a surface of no return. Once you cross it, all paths lead inward. Space-time is curved so extremely that even traveling at light speed away from the center, you still move inward, trapped by geometry rather than force. And the outside universe fades away. Time and space swap roles inside the horizon in strange ways relativity predicts. White holes are the theoretical opposite, never observed but mathematically possible. Regions where matter and light can only exit, nothing can enter, a one-way boundary reversed, and everything inside eventually erupts outward, expelled into the surrounding space. And if they exist, they'd be incredibly unstable, probably existing only briefly before collapsing or transforming into something else. Einstein-Rosen bridges originally connected a black hole to a white hole, with a wormhole throat between them. And in this geometry, matter falls into the black hole, travels through the wormhole, and erupts from the white hole elsewhere, a cosmic plumbing system connecting distant regions through curved space-time. But the problem is that these wormholes collapse before anything can pass through. The throat pinches shut almost instantly, faster than light can travel through it, and anything inside gets crushed, caught in the collapsing geometry. So these natural Einstein-Rosen bridges are not traversable, merely mathematical curiosities that don't allow actual travel through them. Traversable wormholes, the kind we've been imagining, are different. They require exotic matter to hold them open, and they don't have event horizons, no point of no return. You can travel through in either direction freely, entering one mouth and emerging from the other, or going back the way you came, passing through as many times as you want without being trapped. This is the crucial difference between wormholes and black holes. Black holes have horizons that trap you, wormholes ideally don't, and this makes wormholes useful for travel while black holes are dangerous, one-way trips to destruction, unless there's something strange inside that we don't understand yet. Some solutions to Einstein's equations involve rotating black holes, called Kerr black holes, and these have a different interior structure. Instead of a point singularity at the center, they have a ring singularity, a circular line of infinite density rather than a point. And mathematically, you might pass through the ring without hitting it. If you could do this, you might emerge somewhere else, not crushed, perhaps entering another region of space-time or even another universe, and the Kerr geometry allows this mathematically, but whether it works physically remains unknown because we can't test it. We can't send probes into black holes and retrieve them to report what they found inside the event horizon. The singularity is where Einstein's equations break down, predicting infinite density and curvature. And most physicists believe that quantum effects not included in general relativity would prevent true infinities, that something else happens at the center, perhaps a quantum structure or a bounce that connects to another region rather than ending in a singularity. But we need a theory of quantum gravity. White holes might be connected to the Big Bang itself. Some cosmologists speculate that the Big Bang was like a white hole erupting into existence, matter and energy pouring outward into the new universe. And perhaps wormholes connect our universe to others, each Big Bang the white hole end of a wormhole, whose black hole end exists in a parent universe, an infinite chain of universes birthing each other through wormhole connections. These ideas are highly speculative, far beyond what we can test, but they show how wormholes fit into broader questions about spacetime, about the origin of the universe, about whether reality is one cosmos or many, about whether black holes destroy information or preserve it by sending it somewhere else through hidden passages we haven't discovered yet. From the outside, telling a wormhole from a black hole would be difficult. Both create similar gravitational lensing, both bend light around them, but careful observation would reveal differences, because light can pass through a wormhole while it vanishes into a black hole, creating different patterns in the distorted starlight that astronomers could potentially measure and distinguish with precise instruments. If you approached a black hole and a wormhole side by side, the black hole would appear completely dark at its center, an absolute void where the event horizon swallows everything, while the wormhole would show light from the other side, a view of the destination, making it look like a window or lens onto distant space rather than a dark trap. The tidal forces would also differ in some cases. Stable, traversable wormholes might have gentler tidal forces near the mouth, designed to let travelers pass safely, while black holes have enormous tidal forces that increase rapidly as you approach, stretching anything that falls in, pulling it apart long before reaching the event horizon, unless the black hole is supermassive and huge. For now, these comparisons are mostly theoretical. We've observed black holes, seen their effects, imaged their shadows, detected gravitational waves from their collisions, but we've never observed a wormhole or white hole, never confirmed that anything except black holes actually exists in nature, though the mathematics allows all three, suggesting that spacetime is richer, more varied than what we've discovered so far. Understanding the differences prepares us for future discoveries. so that when we observe something unusual, something that doesn't quite match black hole predictions, we'll consider whether it might be a wormhole, whether we're seeing the signature of a traversable tunnel rather than a one-way trap, whether nature has provided shortcuts alongside the dead ends, connections alongside the singularities. And if we find a wormhole, we'll need to study it carefully before attempting passage, measuring its stability, checking for exotic matter, confirming it's not collapsing, ensuring it doesn't lead to a dangerous destination, testing with probes before sending humans, learning everything we can about this structure that offers passage through space-time, but might also present risks we can't fully anticipate without direct experience and observation. The universe holds many mysteries, and wormholes are among the deepest, structures that connect fundamental physics to cosmic engineering, that link mathematical beauty to practical possibility, that challenge our understanding of space, time, causality, and reality, inviting us to explore not just with telescopes and equations, but eventually perhaps with spacecraft passing through to see what lies on the other side. How would we actually find a wormhole if one exists in our galaxy? What specific signatures would reveal its presence? What observations would distinguish it from ordinary objects? And what instruments do we need to search effectively, to scan the cosmos for these elusive structures that might be hiding among the billions of stars and countless cosmic phenomena? Gravitational lensing is the primary detection method, because wormholes bend light, creating multiple images of background stars or distorting their positions, and by carefully mapping how light bends around an object, we can infer the space-time geometry, determining whether we're seeing a black hole, a star, or potentially a wormhole with its distinctive pattern of light from both mouths mixing together. The key difference is that wormholes allow light to pass through. So unlike black holes where light spirals inward and vanishes, wormholes would show light emerging from the throat, creating a complex lensing pattern where stars from the other side appear mixed with stars behind the wormhole mouth, a double image effect that careful spectroscopy and position measurements could potentially reveal. Astronomers would need to observe the same region repeatedly over time, watching for consistency in the lensing pattern, because a wormhole should create stable distortions that don't change like gravitational lensing from a moving object would, and the spectrum of light coming through should match distant regions, not local sources, indicating that photons traveled through space-time from far away. Gravitational waves offer another detection avenue, because wormholes would have distinct signatures if matter passes through them, creating ripples in space-time that differ from black hole mergers or neutron star collisions. And as our gravitational wave detectors become more sensitive, we might identify signals that match wormhole predictions rather than known sources, pointing to structures we haven't confirmed yet. If a wormhole existed and something massive passed through it, perhaps a star or gas cloud entering one mouth, the event would create gravitational waves as matter accelerated through the curved throat, and these waves would have a distinctive pattern, a signature that theorists have calculated, giving us a template to search for in the data stream from LIGO, Virgo, and future detectors like LISA in space. Cosmic rays might also provide clues. High-energy particles traveling through the galaxy occasionally, and if some pass through wormholes, their arrival directions wouldn't match their sources, creating anomalies in the cosmic ray map where particles seem to come from the wrong direction, having taken a shortcut through a wormhole rather than traveling directly across space in a straight line. This would be subtle, requiring careful analysis of thousands of cosmic ray events, looking for statistical patterns that suggest some particles traveled through hidden passages, and while individual cases would be ambiguous, a cluster of anomalies from one region might indicate a wormhole mouth in that direction, a shortcut that particles occasionally find and traverse before reaching Earth's detectors. Stellar orbits near suspected wormholes would show peculiar behavior. Stars circling the wormhole mouth would experience gravitational effects from both ends, including the mass distribution at the distant mouth thousands of light years away, creating orbital anomalies that don't match predictions for a single concentrated mass. Subtle deviations that precise astrometry over years or decades might reveal. We're already monitoring stars near the galactic center with incredible precision, measuring their orbits around Sagittarius A star to test general relativity. And if a wormhole existed there, the orbits might show tiny unexplained accelerations or perturbations that suggest additional gravitational sources or unusual space-time geometry beyond what a simple black hole produces, hinting at more complex structure hidden in that extreme environment. Spectroscopy of light coming through a wormhole would be revealing, because the light might show redshift or blue shift from the distant source, and if we compare that to the wormhole's location, we might find mismatches, light that's redshifted, as if coming from a galaxy thousands of light years away, but appearing to originate from a nearby point, indicating it traveled through space-time rather than through normal space. Dust and gas near a wormhole mouth would behave strangely, potentially spiraling into one mouth and emerging from the other, creating flows that don't make sense locally, but would make sense if matter is being transported. And observing such flows, mapping where material goes, might reveal that it's vanishing here and appearing elsewhere, connected by an invisible tunnel through space-time. The searches continue with every new telescope, every improved detector. Astronomers catalogue millions of objects, measuring their properties, and automated algorithms scan for anomalies, for anything that doesn't fit known categories, that might be something new, and one day an algorithm might flag an object that matches wormhole predictions, triggering intense follow-up observations to confirm whether we've found one. Space-based telescopes would be ideal for this search because they avoid atmospheric distortion and can observe continuously without day-night cycles, staring at suspected regions for months, building detailed maps of gravitational lensing patterns with precision impossible from Earth, potentially resolving the subtle differences between wormholes and black holes that ground-based telescopes can't distinguish reliably. The James Webb Space Telescope and future instruments will contribute. Observing in infrared where dust is transparent, seeing through the galactic disk to regions we can't easily study in visible light, and if wormholes exist in crowded regions or behind dust clouds, these instruments might finally see them, revealing structures that have been hidden from our telescopes until now. Amateur astronomers might even contribute to the search, analyzing public data, participating in citizen science projects that distribute analysis tasks to thousands of volunteers, and someone working from home might spot an anomaly, a lensing pattern that professionals missed, leading to the discovery that wormholes exist, that the universe provides these passages, that distance is not as absolute as we thought. Discovery would transform astronomy immediately. Every telescope would turn toward the wormhole. Every instrument would study it, measuring its size, stability, gravitational effects, searching for exotic matter, determining whether it's traversable or just a curiosity, whether it connects to somewhere useful or to an empty void, whether nature has given us a gift or just a puzzle to solve, a structure we can observe but not yet use. And if it proves traversable, if studies confirm it's stable and safe, humanity would begin planning missions, designing probes that could pass through, carrying instruments to measure conditions inside the throat and at the destination, sending back data through the wormhole itself, using it as a communication link as well as a passage, and eventually, if everything checks out, preparing to send humans through, the first travelers to cross space-time shortcuts. That moment would be historic, comparable to the first moon landing or the first voyage across an ocean. Humans stepping through a wormhole, disappearing from one point and emerging light years away in moments, proving that the universe is more navigable than we dreamed, that shortcuts exist and that humanity can use them, that we're ready to become a truly galactic civilization, spread across vast distances but connected by passages through space-time. Until then, we search, we watch, we analyze, and we prepare, so that when the moment comes, when discovery arrives, we'll be ready, we'll understand what we're seeing, we'll know what questions to ask, and we'll take the next steps confidently, moving from theory to exploration, from equations to experience, from imagining wormholes to actually traveling through them. Imagine the future, centuries ahead, where humanity has found or built wormholes, where the galaxy is no longer a vast, inaccessible wilderness, but a connected network, where every human settlement is just moments away from every other, where distance means almost nothing, and the species thrives across thousands of light years, united by passages through space-time. Children in that future would grow up with wormholes as normal, as ordinary as highways or airports to us, and they'd study space-time geometry in school, learning how wormholes work, how they're maintained, understanding that space has hidden dimensions and connections, that the universe is richer than flat geometry suggests, structured with shortcuts and passages. Space travel would split into two categories. Conventional travel within a star system, moving from planet to planet using rockets, and wormhole travel between systems, stepping through mouths to cross light years instantly. And people would think of the galaxy in terms of the wormhole network, planning routes through multiple hops, considering which connections exist and where they lead, navigating by connectivity rather than distance. A journey from Earth to a colony 10,000 light-years away might involve 3 wormhole transits: Earth to Vega, Vega to Sagittarius A star, Sagittarius A star to the destination colony, each hop taking seconds. The entire journey may be 10 minutes, including time to navigate through each system, and travelers would barely have time to adjust before arriving, crossing distances that once seemed impossible. Tourism would flourish, with agencies offering grand tours of the galaxy, visiting famous nebulae, watching supernovae from safe distances, touring the galactic center's star clusters, witnessing black holes up close and returning home the same day, having seen wonders that previous generations could only dream about, bringing back images and experiences from across the cosmos. Scientists would have unprecedented access to phenomena they currently observe remotely, studying pulsars up close, sampling nebula gas directly, monitoring stellar evolution by visiting the same star cluster repeatedly over years, placing instruments in exotic locations and retrieving them whenever needed, transforming astronomy from passive observation to active exploration, hands-on investigation of cosmic mysteries. Economic activity would span the galaxy, with trade flowing through wormholes, resources from one system supporting industries in another, and specialized worlds developing based on local conditions. One planet becoming the manufacturing hub, another the agricultural center, a third focused on research, each contributing to the galactic economy, connected by instant transport that makes interstellar trade practical and profitable. Cultural exchange would be continuous. Artists from one world inspiring audiences on another, students studying at universities light years from home, returning for holidays through wormholes, and families staying connected despite being scattered across the galaxy, able to visit each other regularly, maintaining relationships that distance would otherwise destroy, keeping humanity unified across the stars. Governance would face interesting challenges, because wormholes make distance irrelevant but raise questions about control, about who owns the wormhole mouths, who decides where they connect, whether travel through them is free or requires fees, and political structures would need to adapt, perhaps creating galactic councils that manage the network, ensuring fair access, preventing any one faction from controlling critical passages and dominating the system. Military considerations would be significant, because wormholes are strategic choke points, and controlling them means controlling movement across vast regions, making them targets during conflicts and requiring protection, leading to orbital stations around each mouth, defense systems monitoring who passes through, ensuring security while maintaining open access for legitimate travelers who pose no threat. Colonization would accelerate dramatically, because establishing new settlements becomes easier when supplies and people can flow through wormholes, and if a colony encounters problems, help arrives instantly rather than years later, making frontier worlds less isolated, less risky, more appealing to settlers who know they're not permanently cut off from civilization, just a wormhole hop away from Earth and the established worlds. Humanity would spread to regions currently unreachable, exploring the galactic halo, visiting globular clusters at the Milky Way's edge, establishing outposts in the outer disk, and eventually, if wormholes can connect to other galaxies, expanding beyond the Milky Way entirely, to Andromeda and the local group, becoming a truly intergalactic species, scattered across millions of light years but still connected, still one civilization united by technology that defeats the tyranny of distance. Environmental benefits might emerge too, because instant transport means less reliance on generation ships, less need to terraform marginal worlds when you can easily visit better ones, less pressure on any single planet because resources flow freely through the network, distributing the burden of supporting civilization across many worlds rather than concentrating everything on Earth or a few colonies, preserving pristine worlds while developing others. Education would be transformed. Students could attend the best universities regardless of location, visiting campuses light years away daily, and scholars would collaborate in person despite living on different worlds, working together on projects, conducting research that draws on expertise scattered across the galaxy, assembling teams of the best minds without requiring anyone to relocate permanently, just commute through wormholes. Art and culture would explode with diversity, as different colonies develop unique traditions influenced by their environments, and artists could tour the galaxy, performing on dozens of worlds, sharing their work with audiences everywhere, while others could experience the full range of human creativity by hopping through wormholes to festivals, galleries, performances happening on distant planets, all accessible within hours. Healthcare would improve dramatically. Medical specialists available anywhere through wormholes, patients able to visit the best hospitals regardless of location, and medical supplies transported instantly, ensuring every world has access to cutting-edge treatment, vaccines, equipment, even if they're newly settled and lack local infrastructure. The network providing support that makes frontier life safer, more sustainable, more humane. This future might seem like fantasy, impossibly distant, but every step forward brings it closer. Every discovery about space-time adds knowledge, and perhaps our descendants 5 centuries from now will look back at our era with fondness, remembering when humans were confined to one star system, before wormholes opened the galaxy, before distance ceased to matter, when humanity was young and the cosmos still seemed vast and unreachable. They might preserve Earth as a historical site, the cradle world, protected from overdevelopment, visited by pilgrims from across the galaxy who come through wormholes to walk where the species evolved, to see the sky their ancestors saw, to connect with origins before spreading across light years. And they'd marvel at how small our world once felt, how limited we were before tunnels through space-time expanded our reach beyond anything we could imagine. Or perhaps they'll still be searching, still waiting for the first wormhole, studying, calculating, building, working toward that breakthrough. And this vision of a connected galaxy remains a dream, a goal, something to strive for across generations, motivating exploration, pushing science forward, giving humanity purpose beyond our single world, beyond our brief lives, a project that spans centuries, uniting us in shared ambition to make the galaxy truly ours. Either way, thinking about wormholes changes how we see the universe, making it feel less hostile, less impossibly large, more structured, potentially more accessible. And that matters because hope matters, vision matters, believing that distance isn't absolute, that shortcuts might exist, that the cosmos might be kinder than empty space suggests, offering passages for species clever enough to find them or build them. Either way, thinking about wormholes changes how we see the universe, making it feel less hostile, less impossibly large, more structured, potentially more accessible. And that matters because hope matters, vision matters, believing that distance isn't absolute, that shortcuts might exist, that the cosmos might be kinder than empty space suggests, offering passages for species clever enough to find them or build them. Wormholes represent humanity's deepest longing, the desire to transcend limits, to overcome obstacles that seem insurmountable, to find ways around barriers that nature places before us. And whether they exist or not, the fact that we can conceive them, that the mathematics allows them, tells us something profound about the universe, about its flexibility, its hidden possibilities. The universe is stranger than we imagined a century ago, before Einstein showed us that space and time are woven together, that gravity bends space-time, that the fabric of reality is dynamic, curved, and potentially structured in ways we haven't fully explored, with shortcuts and connections we're only beginning to understand through mathematics, observation, and careful theoretical work. Every time we push deeper into physics, we find new surprises. Quantum mechanics revealed particles behaving in impossible ways. General relativity showed time flowing differently at different speeds and locations. And these discoveries transformed technology, enabling GPS satellites, nuclear power, modern electronics, proving that understanding reality deeply has practical consequences beyond pure intellectual satisfaction. Wormholes sit at the frontier of our knowledge, where general relativity meets quantum mechanics, where theoretical predictions push beyond what we can currently test. And studying them forces us to think carefully about spacetime's structure, about causality, about what's fundamentally possible versus what merely seems impossible from our limited perspective on this one planet orbiting one star in a galaxy of billions. They challenge our assumptions about reality. The idea that here and there are fundamentally separate, that distance always matters, that the past is unchangeable and the future unreachable, and questioning these assumptions, entertaining possibilities that violate common sense, is how science progresses, how we move from Newton's gravity to Einstein's curved spacetime, from classical physics to quantum weirdness. If wormholes exist naturally, the universe has structure we haven't discovered, hidden connections threading through space-time, perhaps left over from the Big Bang, perhaps forming during black hole collisions, structures that could revolutionize physics if we find them, proving theories we can currently only test mathematically, opening new areas of research into space-time's properties and behavior. If they can only be built artificially, that's equally profound, because it means sufficiently advanced civilizations can manipulate space-time itself, can engineer the fabric of reality, bending it to their purposes, creating infrastructure on cosmic scales, and that possibility expands our vision of what intelligence might achieve given enough time, enough knowledge, enough technological capability. Either outcome teaches us something crucial about the universe, about whether nature provides shortcuts or whether they require intelligent intervention, about how flexible space-time is, how responsive to manipulation. And these questions connect to others we're exploring, about dark energy, about quantum gravity, about the ultimate structure of reality at scales we can't yet probe directly with experiments. The search for wormholes is also a search for ourselves, for what humanity might become, for what we're capable of achieving if we survive long enough, advance far enough, and the vision of traveling through wormholes, of building networks across the galaxy, gives us something to work toward, a goal that transcends our brief individual lives, connecting us to a larger project spanning generations. This kind of thinking matters, especially in difficult times, when problems seem overwhelming, when the future feels uncertain. Having grand visions reminds us that humanity has potential, that we've come from caves to spacecraft in a geological eye blink, and that given time, given dedication, we might achieve things that currently seem impossible, that the cosmos might one day be our home rather than an unreachable wilderness we can only observe from afar. Wormholes inspire scientists and dreamers alike, appearing in research papers and science fiction, in university classrooms and blockbuster movies, and this cross-pollination between rigorous science and popular imagination helps both, because scientists need to communicate their discoveries, and the public needs to understand what's real, what's speculative, what's purely fictional, and where the boundaries lie between these categories. Young people inspired by wormhole stories might study physics, become the scientists who finally find one or prove they're impossible, and even if they choose other paths, they'll carry with them a sense of wonder about the universe, an appreciation for how strange and beautiful reality is, how much we've learned and how much remains mysterious, waiting for future generations to explore and understand. Education benefits from having big questions to teach. Because students engage more deeply when topics connect to fundamental mysteries, and wormholes provide that, a hook for teaching general relativity, space-time geometry, exotic matter, quantum mechanics, all wrapped in a narrative about cosmic shortcuts that captures imagination while delivering real physics, accurate mathematics, honest discussions of what we know and don't know. The possibility of time travel through wormholes raises profound philosophical questions about free will, causality, the nature of time, whether the past is fixed or flexible, whether we exist in one timeline or many, and these questions don't have easy answers. They push us to think carefully about assumptions we usually take for granted, about how reality is structured at its deepest level. If closed time-like curves exist, paths through space-time that loop back, then an event could influence its own past, creating loops of causation without clear beginning. And while physics offers frameworks like the Novikov principle or many worlds interpretation to handle this, none feels completely satisfying. None resolves all the puzzles, leaving us uncertain about whether time travel is truly possible or whether nature has protections we haven't discovered yet. These uncertainties are humbling but also exciting because they mean we don't have all the answers, that there's still work to do, discoveries to make, and each generation of physicists pushes a little farther, resolves some questions while uncovering new ones, and the process continues, building knowledge piece by piece across centuries, each contribution adding to the structure that future scientists will inherit and extend further. Wormholes also connect to the search for a theory of quantum gravity, because understanding them fully requires unifying general relativity with quantum mechanics. Two frameworks that work brilliantly in their domains but clash at extremes, at singularities, at tiny scales where both matter, and resolving these clashes might reveal whether wormholes can really exist, whether quantum effects stabilize or destroy them, questions we can't answer until we have that unified theory. String theory, loop quantum gravity, and other approaches attempt this unification. And some predict microscopic wormholes, quantum foam connecting points at Planck scales, structures too small to traverse, but possibly detectable through their effects on particles or fields. And finding evidence for these would validate not just wormholes, but entire theoretical frameworks that currently rest on mathematics alone, unproven by experiment. The fact that we can ask these questions, can calculate possibilities, shows how far science has come. And 1,000 years ago, people couldn't even conceive these ideas, didn't know about space-time or quantum mechanics or relativity. And today we debate whether shortcuts through space-time exist, whether time travel is possible, questions that would sound like magic to our ancestors, but are legitimate physics to us, problems addressed with equations and observations. Progress accumulates slowly, sometimes frustratingly so. Decades pass between major breakthroughs, careers spent on problems that remain unsolved, but each effort contributes, each calculation adds to the foundation, and suddenly someone sees a connection, makes a discovery, and the field leaps forward, transforming what's possible, opening new areas to explore. And the cycle continues, science advancing through collective effort across generations. We might not find or build wormholes in our lifetimes, but the work we do now, the questions we ask, the theories we develop, will inform future scientists who might succeed where we couldn't, who will have better instruments, better mathematics, better understanding of space-time, building on foundations we're laying today, even if we never see the final result ourselves. This long-term view matters because it contextualizes our efforts. We're part of something larger than ourselves, a multi-generational project to understand reality. And whether we find wormholes or not, the attempt teaches us about space-time, pushes technology forward, trains new scientists, expands human knowledge, all valuable outcomes regardless of whether the original goal is achieved or proves impossible. And there's beauty in the uncertainty, in not knowing yet, because it means the universe still holds secrets, still surprises us. And there's something wonderful about living in an era where fundamental questions remain open, where we can still discover new structures, new phenomena, where reality hasn't been completely mapped and catalogued, where mystery persists alongside knowledge, inviting exploration. Wormholes embody that mystery beautifully. They're mathematically predicted, but unobserved, theoretically possible, but practically uncertain, and they represent the edge of our knowledge, the frontier where equations meet reality, where speculation becomes testable, and whether nature grants or denies their existence, the answer will teach us something profound about the universe's structure and the limits of what space-time geometry allows. In imagining them tonight, in traveling through wormholes mentally, we've engaged with some of the deepest ideas in physics, thought about space and time as flexible structures, considered causality and paradoxes, and this mental exercise, this visualization of impossible journeys, helps us grasp concepts that defy everyday intuition, training our minds to think in ways that let us understand the cosmos more deeply, more accurately than common sense alone allows. Whether you've stayed awake through all of this or drifted off earlier, the ideas have passed through your mind, and some might linger, surfacing in dreams or quiet moments. And that's valuable too, because understanding grows over time, percolating through consciousness, and concepts that seemed strange tonight might feel familiar tomorrow, integrated into your worldview, changing how you see the universe and your place within it. As we approach the end of this journey, I want you to feel satisfied, not rushed, not pressured, just aware that we've explored something beautiful together, traveled through imagination to places light takes millennia to reach, crossed distances in moments through tunnels in space-time, and whether these journeys ever become real or remain forever theoretical, they've shown us what might be possible, what the universe might allow, what future generations might achieve if they continue pushing forward, exploring deeper, reaching farther than we can. Now, as we near the end of this 2-hour journey, it's time to begin returning home, to step back through the wormhole of imagination and find yourself again in this quiet room, in this moment, on this planet, under this particular sky that you might look up at later and see differently, more deeply, with new appreciation for the vast, strange cosmos spinning around us. We've traveled far tonight in thought, if not in body, crossing the galaxy through wormholes, emerging in distant star systems, witnessing alien skies, moving through time itself, and then understanding the science, learning how space-time curves, how Einstein's equations allow these passages, why exotic matter matters, what challenges prevent us from building or finding them, all while staying here, safe, comfortable, drifting towards sleep. The wormholes we imagined are scientifically grounded, based on real mathematics, genuine solutions to Einstein's field equations, not fantasy, but extrapolation from what we know about gravity, space-time, and the universe's structure. And while we added speculation about networks and time travel and future civilizations, the foundation is solid, rooted in physics that's been tested and confirmed in countless experiments. This blend of science and imagination is valuable because it shows what might be possible, what future discoveries could reveal, what humanity might achieve given enough time, and it connects abstract equations to human experience, to the desire to explore, to transcend limits, to find shortcuts through the vast cosmos that currently seems so forbiddingly large, so impossibly distant from our small blue planet. If wormholes never exist beyond mathematics, we've still gained something. Deeper understanding of space-time, appreciation for the universe's strangeness, vision of what advanced civilizations might do, and these insights matter. They expand our minds, stretch our sense of possibility, remind us that reality is richer than everyday experience suggests, structured in ways that require careful thought and study to comprehend fully. And if wormholes do exist, if they're found or built someday, then tonight you've previewed that future. You've experienced in imagination what your descendants might experience in reality, and you'll remember this quiet evening when the possibility seemed distant, uncertain, a dream that might or might not come true, and perhaps you'll tell someone about it, sharing the vision, spreading the hope that distance might not be absolute, that the stars might be reachable after all, that shortcuts exist for species clever enough to find them or patient enough to build them over generations. The universe is vast, so large that light from distant galaxies has been traveling billions of years to reach us, and what we see when we look at those galaxies is ancient light, showing us how they looked in the deep past. And this means the observable universe is limited not just by space, but by time, by how long light has had to travel since the Big Bang, creating a cosmic horizon beyond which we cannot see, a boundary that makes the universe feel even larger, even more isolated. But wormholes, if they exist, might pierce that horizon, connecting distant regions that light hasn't had time to link, bringing together parts of the universe that seem forever separated. And this is both wonderful and slightly unsettling, because it means our intuitions about distance and causality might be wrong, that the cosmos might be more connected, more intimate, more accessible than the vastness of space suggests when we look up at night and see only distant pinpoints of light. Part of the appeal of wormholes is philosophical. They represent hope that the universe isn't indifferent, that it might contain passages for explorers, that intelligence and curiosity might be rewarded with access to wonders currently out of reach. And while the universe doesn't care about human desires, doesn't owe us shortcuts, the possibility that physics allows them feels encouraging, suggesting that nature is more generous than the harsh reality of distance and the speed of light limit would imply. We're pattern-seeking creatures, we humans, constantly looking for meaning, for connections, for ways to understand and navigate the world, and wormholes fit that pattern, their connections, literal links through space that would let us navigate the cosmos. And maybe that's why they fascinate us so deeply. Beyond the science, beyond the equations, they appeal to something fundamental in how we think, our need to find paths, to make the distant near, to bring things together that seem separated. In our daily lives, we build connections constantly, roads, bridges, internet links, all infrastructure designed to defeat distance, to let us communicate and travel efficiently, and wormholes would be the ultimate extension of this impulse. Cosmic infrastructure connecting not cities but star systems, not computers but entire civilizations, the grandest engineering project imaginable, turning the galaxy into a neighborhood where everywhere is accessible, where no world is too remote to visit. This projection of human needs onto cosmic scales is revealing. It shows what we value, what we long for, connectedness over isolation, access over limitation, and studying wormholes, thinking about them seriously, allows us to explore these values through science, to ask whether the universe accommodates our desires or, indifferently, enforces barriers we cannot overcome, and either answer teaches us something about reality and our place within it. Tonight, you've engaged with these ideas gently. No pressure to memorize, no test at the end, just exposure to concepts that might change how you see the night sky, how you think about distance and space, and as you drift towards sleep, these thoughts might transform into dreams, wormholes becoming doorways in your sleeping mind, passages through which you travel to strange places, alien worlds, different times, your subconscious playing with the ideas we've explored, weaving them into narratives that feel real until you wake. Dreams are their own kind of wormhole, connecting different parts of your mind, bringing together memories and imagination, creating experiences that seem real despite being impossible. And in that sense, you travel through wormholes every night, shortcuts through your inner space, passages between different states of consciousness, and maybe that's another reason these ideas resonate. They echo something we already know about how minds work, how thoughts connect across gaps that shouldn't be crossable. The metaphor extends further if you let it. Books are wormholes connecting you to authors separated by time and space. Music connects you to emotions others felt, and language itself is a kind of wormhole, allowing ideas to pass from one mind to another, thoughts that originated in someone else's consciousness now existing in yours, connected by words, by symbols that somehow bridge the gap between separate beings. Maybe wormholes in space-time are just another version of this. Connections that shouldn't work but do, shortcuts that violate apparent rules, but might be allowed by deeper principles, and thinking about them expands our sense of what connection means. These late-night thoughts might seem strange, too abstract, but they're natural when you think deeply about space-time, about what it means for distant points to connect, about whether reality is fundamentally separated or secretly unified. And philosophers have wrestled with similar questions for millennia, only now we have mathematics and physics to guide speculation, to ground intuition in calculation, to test whether ideas match how the universe actually behaves rather than just how we wish it would. As sleep approaches, I want to offer you a final visualization, a gentle image to carry into dreams, something peaceful and beautiful, drawing together everything we've explored tonight into one coherent picture that your mind can hold without effort, without strain, just a simple scene that summarizes the journey, the hope, the wonder we've touched on through these hours together. Picture yourself standing at the entrance to a wormhole, in a spacecraft or station, looking through a window at the mouth, a sphere of distorted space hovering before you, and through it, you see another place, distant stars, unfamiliar constellations, a destination thousands of light years away, visible through the tunnel, close enough to touch despite the enormous distance that normally separates these 2 points in the galaxy. The wormhole is stable, gently glowing with some kind of exotic energy, and you know it's safe, that others have traveled through before, that stepping through means you'll cross the galaxy in moments, and you feel excited but also peaceful, because this is normal in this imagined future, routine, and you're about to take a journey that would have been impossible for your ancestors, a trip they could only dream about, but for you, it's just another day, another passage through space-time, another confirmation that the universe is navigable, that shortcuts exist. You step forward, crossing the threshold, And for a moment, everything shifts. Space bends around you, light from both ends mixing in strange patterns. And you're inside the throat, floating through curved geometry that connects distant regions, and it feels like falling and flying simultaneously, like being everywhere and nowhere, time stretching and compressing. And then you emerge on the other side, thousands of light years away, arriving in an instant, having crossed the galaxy without crossing all the space between. And you're home, or at least at your destination, and the wormhole closes gently behind you, or stays open, waiting for the next traveler, for the next passage, perpetually connecting, forever bridging the gap. This image, this peaceful scene, is what I want to leave you with, not the equations or the challenges or the uncertainties, just the simple beauty of the idea, the hope that distance might not be absolute, that the cosmos might be kinder, more structured, more navigable than it seems. And whether this comes true or remains forever imagination, the vision itself has value. It expands what we think is possible, what we might achieve, what the universe might allow. As you drift towards sleep now, let that image fade softly. The wormhole becoming dimmer, the stars growing distant, and you're back in this room, in this moment, comfortable and safe. And the journey was just a dream, just imagination, but it was a good dream. Wasn't it? A hopeful vision. And maybe someday it will be more than that. Maybe it will be reality. And humanity will travel the galaxy through tunnels in space-time, building networks, connecting worlds, making the universe truly home. But for now, it's enough to have thought about it, to have learned something, to have spent these hours exploring ideas that matter, that stretch the mind, that connect us to something larger than our individual lives. And as sleep takes you, gently, slowly, know that you've traveled far tonight, not in body, but in thought. And that counts, it matters, because understanding begins in imagination, in wondering what might be possible, in asking questions about the deepest structure of reality. Thank you for traveling with me tonight, for staying awake this long, or for drifting off earlier and letting the ideas wash over you as you slept. And either way, I hope this was peaceful, restful, educational, whatever you needed it to be. And I hope you'll remember some of this, perhaps not the details, but the feeling, the sense of wonder, the appreciation for how strange and beautiful the universe really is, how much stranger than everyday experience suggests. When you wake, tomorrow or today, depending when you're listening, you might look at the sky differently, might think about space differently, seeing not just distance but potentially connection, not just separation, but maybe hidden passages. And even if you forget most of what we discussed, that shift in perspective remains, that sense that reality is deeper, richer, more mysterious than it appears, and that's worth carrying forward, that awareness of cosmic possibilities. Rest well, sleep deeply, and let your dreams take you wherever they will. Through wormholes or across ordinary space, to distant stars or familiar places, and know that whether you're dreaming or waking, the universe continues its slow dance, stars orbiting, galaxies spinning, and maybe somewhere, hidden in the fabric of space-time, wormholes wait, undiscovered or impossible. We don't know yet, but the mystery remains. The question persists, and future generations will keep searching, keep calculating, keep dreaming of shortcuts through the cosmos. And in that searching, in that dreaming, humanity finds purpose, direction, something to work toward that transcends our brief individual lives. And whether we ever find wormholes or build them or prove they can't exist, the attempt matters, the effort counts, because it pushes us forward, expands our knowledge, unites us in common curiosity about the universe and our place within it. And that's enough. That's valuable. That's worth the centuries of work that this project will require, if it's even possible at all. Sleep now. And in your dreams, travel through wormholes, visit distant stars, cross the galaxy in moments, move through time, explore impossible geometries, and experience what might someday be real. Either way, the journey has value, the dream matters, because we are the dreaming species, the ones who look up and ask how, who wonder what's possible, who refuse to accept that distance is absolute. That refusal to accept limits is what makes us human, what drives us forward, what might someday take us to the stars, through wormholes or through patient journeys across light years. Either way, fulfilling the ancient dream of traveling beyond Earth. We venture into the vast, beautiful, mysterious cosmos that surrounds us, calling us outward, inviting exploration, waiting patiently for us to develop the knowledge, the technology, the wisdom to venture forth and discover what's really out there. What's truly possible, what the universe allows and what it forbids. What shortcuts exist and which remain forever closed, locked behind physics we can't overcome, or waiting for us to find the key. The understanding that opens passages through space-time, making the galaxy home, the cosmos navigable, distance meaningless, and humanity truly a spacefaring species, spread across light years but connected by passages through space-time. United by tunnels that defeat the tyranny of distance, bringing together what space separates, making the universe smaller, more intimate, more ours, more home, and forever calling us forward to explore. Rest peacefully and drift into dreams where wormholes connect distant worlds, where space bends to human will, where the cosmos opens before us, welcoming, accessible, navigable, beautiful, and forever waiting for explorers. Good night, rest peacefully, and when you wake, remember that you traveled tonight, through wormholes in imagination, across space-time in thought, journeying to places light takes millennia to reach, all from this quiet room. Somewhere in the universe, real or theoretical, those passages might exist, waiting for discovery, for exploration, for the day when humanity finally learns to navigate not just planets but space-time itself, bending reality to our purposes, building tunnels through the cosmos, creating infrastructure that makes the stars accessible, turning the galaxy from a vast wilderness into a connected civilization, united across impossible distances by shortcuts through the fabric of reality, by wormholes that bridge the gap, by passages that make everything possible. And maybe, just maybe, that future is waiting, not today, but someday, centuries ahead or millennia, when our descendants look back and remember these early days, when we dreamed of wormholes, when we calculated their properties, when we imagined traveling through them, when we first began to understand that distance might not be absolute, that space-time is flexible, that the universe might hold passages, shortcuts, connections we haven't found yet, but someday will, someday must. Because the dream is too beautiful to abandon, too important, too fundamental to who we are as a species that looks up, wonders and refuses to accept that the cosmos is forever out of reach, forever distant, forever unknowable, believing instead that we can understand, can explore, can build, can travel, can connect. Can make the universe truly ours, one wormhole at a time, one passage through space-time, one shortcut across light years, one step at a time toward a future where distance doesn't matter, where everywhere is near, where the galaxy is home, where wormholes connect us all, where space-time bends to our will, where the cosmos opens before us, welcoming, accessible, navigable, beautiful, and forever waiting. And in that waiting, in that distant future, humanity finds its destiny among the stars, traveling freely, exploring endlessly, connected eternally across the vast, beautiful cosmos.